Hello, tonight I'm going to solve for a collision between M1 and M2 undergoing a perfectly elastic collision. In a perfectly elastic collision, both linear momentum and kinetic energy are conserved. So starting out with the statement of the sum of momentum before is equal to the sum of momentum after for M1 and M2. Therefore, the momentum of M1 V1, plus the momentum of M2 V2, is equal to the momentum of M1 after the collision, M1 V1 prime, plus the momentum of M2 after the collision, M2 V2 prime. Substituting our values for M1 and M2, we get 1 times 3 plus 2 times 0 equals 1 times V1 prime plus 2 times V2 prime. Simplifying further, we get 3 is equal to V1 prime plus 2 V2 prime. I'm going to draw a little box around this. We're going to use this expression later. Now let's work the right-hand side of our workspace. Look at the sum of the kinetic energies for the collision, and they equal the sum of the kinetic energies after the collision. In a similar fashion, the kinetic energy of each mass before and after the collision are as follows: 1/2 M1 V1 squared plus 1/2 M2 V2 squared is equal to 1/2 M1 V1 prime squared plus 1/2 M2 V2 prime squared. Lo and behold, there's a half in each term, therefore we can cancel each of the halves. And substituting our values, we have 1 times 3 squared plus 2 times 0 is equal to 1 times V1 prime squared plus 2 times V2 prime squared. Simplifying further, get 9 is equal to V1 prime squared plus 2 V2 prime squared. Now, I'm going to solve for V1 prime in our linear momentum expression and substitute V1 prime into our kinetic energy expression. So V1 prime is equal to 3 minus 2 V2 prime, and substituting V1 prime into V1 prime squared, we obtain 9 equals the quantity 3 minus 2 V2 prime quantity squared plus 2 V2 prime squared. Now, expanding the quantity 3 minus 2 V2 prime quantity squared, we get 9 minus 3 times negative 2 twice gives us 12 V2 prime plus minus 2 V2 prime squared, which gives us 4 V2 prime squared. And then we're going to add the 2 V2 prime squared to the 4 V2 prime squared eventually. Now, we see that our 9's cancel. That's convenient, because it means we don't have to solve a quadratic equation. So, simplifying further, add 12 V2 prime to both sides, we get 12 V2 prime is equal to 4 V2 prime squared plus 2 V2 prime squared, which gives us 6 V2 prime squared. Now it looks like we can cancel a V2 prime, and we're left with V2 prime is equal to 12 divided by 6, which equals 2 meters per second. Now, that's consistent with what we think is going to happen. You know, here we have M1 colliding with M2, M1 traveling from the left to the right, bumping into M2. So the fact that this our answer is positive 2 meters per second suggests that at least we're on the right track. Now let's substitute V2 prime into our expression over here, okay, to get V1 prime. So V1 prime is equal to 3 minus 2 times 2, and lo and behold, we get -1 meters per second. And that's consistent with M1 colliding with M2. Because M1 is half the mass in M2, it's been our experience that that mass would recoil and travel in the opposite direction after impact. So there you have it, a two-body collision colliding perfectly elastically and needing to use both conservation of linear momentum and conservation of kinetic energy. There you go. All right, have a good evening.